Remember that our goal is to give as many examples as we can of sets that have very different behavior from the usual manifolds that we are used to from calculus or differential geometry. With these examples in hand, the theory that we will talk about later will be more motivated, and we will have the examples to refer back to for comparison reasons. The first higher dimensional, that means living inside R2 or R3 and not R1, example of a Cantor set that we gave was this particular four-corner Cantor set, which is incidentally also the product of two Cantor sets in R1. Of course, product of Cantor sets is one way of obtaining many examples, but how about other completely different examples? Today I'm going to present to you some discussion from section 412 of Mattila's book, Geometry of Sets and Measures, where a very general criteria for computing the dimension of Cantor sets is given that is quite useful. So you will build, as it happened in our previous examples of Cantor sets, you will have a nested sequence of compact sets. So you can have your compact sets in our construction will be cubes. Well, we have to say not cubes exactly, rectangles, so that the sides do not have to agree. So we are talking in n dimension. So we're going to construct some sets inside Rn, and n is at least 2. So in each step we will have only rectangles, or we will only have triangles, or we will have circles, and I think we can even consider other sets, types of sets. So you start with kind of the boring case that you start with just one huge rectangle, say Q0. In next step, we will replace. Remember that we throw away part of the sets in construction of Cantor sets and we preserve certain parts of it. So we will replace Q0 with some of its subsets, with Q1, Q2, up to a finite number QM1. So there will be M1 babies of Q0. So let me take this further down, where each Qi is a subset of Q0. So far we have this picture. So you start with your Q0, and then you have some certain subsets. So this is the first one, Q1. Maybe the next one is here, Q2. Well, my shapes do not resemble. Okay, Q3, and so on. Well, so let's say M1 is Q3 in this case. In the next step, of course, you will construct inductively. So suppose you have proceeded k steps, so that you have I1, I2, up to ik. So you will have a million such cubes at step k, and you fix one of them, and for the next step you will have, so that will be replaced by some of its own babies. So M mk plus 1, so this step k plus 1, will replace q I1, I2, ik. So I'm kind of freezing these first ones. So when I choose my I1 to ik and fix them, I have one particular cube or rectangle. I'm using these, I noticed, interchangeably. And so this is fixed. The same one. And then I run the index j, the new index j, at level k plus 1. So I will have m of k plus 1. So this one is for the index. So mk plus 1 many subsets of that to replace. So here, for example, let's say I have so in this example, also this last picture actually is good because the sides are also not necessarily parallel to the coordinate axis or anything. So for example, we can say this is Q3 and 1 babies of Q3. So Q3 has 2 babies. And this is Q3, 2. Now in turn, this is going to have its own babies. So maybe it in turn has 2. So this, for example, we can say is Q3, 2, and then second baby. And then the first one is Q3, 2, 1. And of course, this will have its own babies and so on. And then we continue this construction. So the goal will be that, actually let me copy this and get rid of that because it's just so annoying to have it here. Okay, so the goal is easy and computable conditions under which we can find the Hausdorff dimension of the resulting Cantor set. And the resulting Cantor set is not just isn't a hand wavy thing. We can precisely say what it is. So you will have we will have the intersection of all steps. So you can go k from 1 to infinity. Because they are nested, it doesn't matter if you start at 0 or 1. And then this will be union of all level k many, all the cubes at level k. So this will be, I must say, all q at level k. So this will be everything at level k, and then because we have nestedness, we have intersection all of them, and that will be the counter set that we will have ultimately, which is non-empty because it's intersection of nested sequence of non-empty counter sets. Okay, so what conditions should we have to be able to find the dimension of that? And this section that I referenced is exactly answering that question. So what happens is we require some geometric properties for the choices. Number one was already mentioned, that the next levels, so I1, I2, Ik, and J is a subset of I1, I2, Ik. So this index is always a subset of the previous one. then the diameters go to 0, and that is expected from what we've seen in other constructions. So what we mean by this is that take the largest cube of level k. So take the maximum of the diameters of q I1 ik over all I1 ik choices. So run all these indices simultaneously, I1 changes, I2 changes, and so on. And these are finite collections, so there's a maximum. And give this the name dk. That means the worst diameter at level k. Then we require that this goes to 0 as k goes to infinity. So this forces a very refined construction that everything will converge to 2 points. Diameters will die down. The next, maybe the most important restriction that we have is that if we add the s power, so this is similar to, so s is some number between n and 0. Maybe let's be safe and not include 0. It's always dangerous. So adding diameters to power s, remember, is what we do for Hausdorff dimension s. And what we require here is that if you have the cube qi1 ik, if again you freeze one of these and you raise that diameter to power s, then it becomes the summation of diameters of all of its babies. So I1 to ik, again the same value here as here. So we add the index, that means we're looking at all the babies of this guy and their diameters we raise to s, and then we sum over j. So m, k plus 1, many of these we had. So we require this to be precisely equal. And then the last condition, which is kind of forcing things not to concentrate, so avoiding too much concentration, is that for every ball B with diameter at least dk, which is the quantity from here, so the kind of the representative diameter for level k. So if you have a ball of at least that much diameter, so that means you're looking at a scale of size dk, then this diameter of B to power s dominates the summation of diameters of all level k cubes. So we have k indices, that means this is a cube of level k. Again, these we raise to power s. Of course, this cannot be true because this is all the level k cubes and this is kind of comparable to only one of them. The reason this is going to be true is that we only add this over those cubes which have non-empty intersection with this ball. So ik is non-empty. So let me, and also we allow a universal C. So for C, independent of ball and of k. So it's a universal constant. So what happens in picture is that if you take a ball of, let's say, at the level of reds. So at the level of reds, this is probably a comparable diameter, because yes. And then this green only intersects this one, so then it's obvious that the diameter of only one of them to power s is bounded by diameter of this ball to power s. But we could also have this ball somewhere here. Now it covers both of them, and now it's a bit more difficult to have the bound, but then we have this constant c. If we take c equal to 2, definitely we have it. Of course, my picture is just initial levels and kind of biased. Of course, I want to have a cleaner picture. You can imagine that things can go crazy, and if I had maybe if I could squeeze in maybe 100 of these red, smaller of course, red rectangles inside that, then I would have to be worried about what happens if I have one ball and how many meets it. So we don't want too many of these level k cubes to come together, and this condition at any scale, at any position, not a scale, sorry, so this is scale k, but at all positions, wherever you pick your ball, if you randomly drop a ball of that size, it doesn't meet too many of those cubes. Okay, so our construction was very intuitive, of course. We had no restriction on particular sizes. In the same level k, you can have several cubes of different sizes. We only care about this largest diameter among them. So we have the babies. It's an obvious, easy requirement. This requirement is very natural. So we said this is the most important one, and also this one. So basically, the last two are the key. The claim, the theorem, is saying that under these conditions, this Cantor set is of Hausdorff dimension S. And it's also one of the good cases that we actually have positive and finite measure for it. Remember that sometimes you can have s-dimensional, but the s-dimensional measure itself could be either infinity or 0. So this is the nicest situation that can happen. This is not proven in the book, and it's left as an exercise. That is what I will also do, because writing proofs for such things gets very tedious, but the ideas involved in a proof are rather simple. So all you have to do, and all that is available to you, is just definition of Hausdorff measure. Okay? That's just very wonderful theorem, because, yeah, we will later see the most important thing about this construction is that we will see later other theorems that immediately give Hausdorff dimension of sets, but the point here is that C does not have to be self-similar. So we will define what is self-similarity mathematically later, and next video in fact, and compute their Hausdorff dimension, but that case doesn't cover this one, because here we don't have per se self-similar sets. Although in dealing with the Cantor sets, usually what we deal with ends up being self-similar, or maybe self-similar sets are just easier to draw. So let's look at some example, and that will be the Sierpinski gasket. Some people also call this Sierpinski triangle, but according to Wikipedia, it's safer to call this the Sierpinski gasket, and then the similar construction that we will give next session is called the Sierpinski triangle. So what happens here is, this is your Q0, which by that I mean the interior of it. So the babies of it will be this here, this one here. These are supposed to be equilateral, so my drawing isn't reflecting that. So this will be Q1, Q2, and then Q3. So for the next ones, they will be these three. So here, 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 and then here, here, and here, and you will keep going like that. So this is in fact a self-similar construction, and the theorem we will cover next video will cover also that, and can be used to give the Hausdorff dimension. But let's test our theorem in this case. Okay, the main two conditions to check. Do we have this condition that summation of diameters of the babies I1, ikj to power s equals the diameter of this thing itself to power s. So of course this can happen like for, and we want to find the right s. Okay, but because of self-similarity, every qi to ik is just a triangle, and it will have three subsets of it. So they will be three. And what is the diameter of the next generation compared to the previous one? Okay, we can ask, what is the diameter of this one here compared to the diameter of the original one? And the answer is that it's this looks like my picture. So 1, 2, 3, 4. It's 1/4 of that one. Let me double check that. Okay, so 1/4 of diameter of its parent, which is I1 to ik to power s. So we have, this is for the number of j's, and we require that to be equal to diameter of qi1 ik to power s. But then this is the same quantity here and here, it cancels out, so you get that 3 times 1/4 to power s must be equal to 1. So I don't know if such an s exists, but these are if and only ifs. And here you just take log, and you will see that log 3 minus s times log 4 must be 0. From this you get that if s is equal to log 3 over log 4, then this condition will be true. About the other condition of being kind of distributed, we can easily see that it holds, because if I drop a ball of comparable diameter to the red ones, you can actually compute exactly the maximum number of different ones that can touch it. So for example, I can just barely touch this one and then go down this way, And I think at most just this one will touch that, and maybe not even that, because if I take, for example, this and take a ball comparable to that diameter, it doesn't even reach that one. So at most actually one ball of scale dk meets one of the sets in level k. But of course it can be calculated even more precisely. So because of these conditions, the theorem tells us, guarantees us, that the Hausdorff dimension of C is log 3 over log 4. Okay. Here we saw that the next generation is like 1/4. So this 1, if this is 0, 1, then it's 0 to 1/4. But we can also take another one. In fact, I want to give... So the four-corner counter set was interesting because it was a one-dimensional set. It had positive and finite Hausdorff 1 measure, but it didn't look like a curve at all. We can do same with the Sierpinski gasket. So what we do is, this time around, let me try to... Okay, equilateral. This time you want to have it here. And here. So you will have... So if 1/4 is changed to 1/3, you will see that this will be log 3 over, again, log 3, and that will give you 1. So you want to have 1/3 here, and then 2/3 here. So your triangles, your baby triangles, will be these ones. So your next level will be the interior of these. Okay, and then the next generation will be this, this, and this. Remember, these don't touch. So that's where actually it's different from the Sierpinski triangle. It's a bit larger because these actually get to touch each other. So the computations all are the same. So again, this will be a set where H1 of C will be finite and positive. So it's a one-dimensional set, but maybe it's intuitively obvious that C is very different from familiar one-dimensional sets, which are rectifiable curves. So if I draw you any curve, C1 curve, this is a one-dimensional object, but then this is also one-dimensional object, but their behavior is quite drastically different. And that is actually what geometric measure theory is trying to make precise, what is being curve-like and opposite of being curve-like. Okay, so since I had this picture also, let's look at the Hausdorff dimension of this one. So this is called Sierpinski carpet. You start with the huge big square, and then you divide it into 9 parts along here and here. So maybe let me change the color. Okay. So you divide this into 9 squares, and then you keep everything except for the center one. So this is then out. Now you have 9 subcubes, and then you repeat this process for each one of them. So if Q0 is the biggest guy here, then it has not 8 subcubes, and then those 8 each has 8 future subcubes. And if we do a similar calculation to this one here, so you will see that the requirement for S is that 8 times, well, diameter of each one of them is 1/3 of the previous generation. So 1/3 of the new 1/3 of the old diameter to power S must add up to old diameter to power S. So they cancel, you get 1. From this you get that S has to be log 8 over log 3, which is strictly less than 2, but also bigger than 1. So this here, what you end up with is some set which is bigger than curves. Its dimension is strictly bigger than 1, but also it doesn't cover any area. Its Lebesgue measure in particular is 0, but also it's even less than that. The dimension is strictly less than 2. Okay, yeah, so that brings us to the end of this beautiful theorem. So general and applies in so many situations. The examples I gave you, again, for simplicity, were, after all, self-similar, but remember that this theorem covers also non-self-similar cases. Okay, see you in next video with self-similar sets. Until then, have a great one. Thank you. And please do not forget to subscribe if you haven't yet. Still, that matters. Thank you so much.